in our last unit, we learned all about work. Remember that work equals force times distance. Okay, that is already on our equation sheet. Now we are going to be introduced to the simple machines, and we're going to see how machines can do work for us. So we're going to continue to use that exact same equation, but we are going to specialize that equation for these different machines. So first off, let's define what is a machine. It is a device that makes work easier. Okay, so it helps humans by making the work easier. It can make the work easier by changing the size of the force that we are exerting, or by changing the direction of the force, or they can do both at the same time, changing the size and the direction of the force. Okay, so remember, a force is anything acting on something, causing it to move. Now, we are going to separate out the different types of forces that we are going to use when we talk about machines. So there's basically two forces that we're concerned with. There's the effort force. This will be F sub E. This is the force that the human applies to the machine. So this is what you do when you use the machine. Then you have the resistance force. This is the F sub R. This is the force that is applied by the machine. So it is what the machine does. Okay, so in all these problems where we're talking about machines, we need to make sure that we are very careful and we know what force we're talking about. Are we talking about the force of what the human is doing to the machine, or are we talking about the force of what the machine is doing to the object that we're trying to move? Okay, so that's where a lot of people get their math mixed up because they put their numbers in the wrong place. So be very, very careful. Make sure you understand that. So that means with the machine that we have two types of work. We have the work input. This is what the human does. This is the work done on the machine. Okay, this equation should look very familiar. Work equals force times distance. But now we're going to be a little more specific. We're going to say this is the work input because it is the effort force times the effort distance. And then we have the work output. This is the work done by the machine. Same equation, but being more specific about what's going on within it. So the work output is the resistance force times the resistant distance. Okay, so exact same equation, but you just got to be careful and separate out what is the human doing to the machine and what is the machine doing to the object. Remember, with conservation of energy, that you cannot get out more work than what you put in, okay? You have a trade-off between the force being applied and the distance is being applied over, okay? So, but with conservation of energy, that means that the work input and the work output are equal. Okay, so the effort force times the effort distance has to equal the resistant force times the resistance distance. Now, in an ideal machine, so in an ideal world where everything works exactly the way that it's supposed to, then the work input would exactly equal the work output. However, as we have been learning in our last few units, that in the real world this doesn't happen. You don't have that perfect work in to work out ratio because we lose some energy to friction. We learned about this when we learned about energy. When we convert between potential energy and kinetic energy, they should be equal. But they're not perfectly equal because we lose a little bit of energy to friction. All right, so here's our new equation for today. It is the mechanical advantage equation. So this is telling us how much help is this machine really giving us? Okay, that's the mechanical advantage. So we've got the IMA, that's the ideal mechanical advantage. This is in the perfect world where everything goes exactly right. We are going to do the effort distance, so the human's input, divided by the resistance distance, so the distance that the machine moves. Okay? And still using our triangle, this is what that triangle would look like. So you can go ahead and add this to your equation sheet that we have been growing. IMA stands for ideal mechanical advantage. And this is one of those rare numbers, one of those rare calculations where you do not have a unit. Okay, ideal mechanical advantage does not have a unit, it is just a number. D is for distance, so this is going to be measured in meters. Meters. Okay. We also have actual mechanical advantage. So this is in the real world. How much advantage, how much help is this machine giving us? The actual mechanical advantage is AMA, and it is equal to the resistance force, so the force of the machine, divided by the effort force, so the effort, the human force. Okay? So like always, just like before, the mechanical advantage does not have a unit, okay, because you're dividing force by force, so it cancels each other out. But like it always has, force is still going to be measured in newtons, okay, so you're still going to have newtons there. If after you calculate your mechanical advantage, if the number you calculate is greater than 1, that means that you have increased the force by using the machine. If your mechanical advantage that you calculate is less than 1, that means that you are increasing the distance by using the machine. And if it is exactly equal to 1, then the only thing you're doing is changing the direction of the force. Okay? So here is your triangle for AMA, actual mechanical advantage. So be sure to add this to that equation sheet as well, including those units. Now let's do a couple of example problems. A worker applies an effort force of 20 newtons to open a window with a resistance force of 500 newtons. What is the crowbar's mechanical advantage? Okay, so like we always do, let's analyze what we've been given. Okay, we have an effort force of 20 newtons. So the worker applies 20 newtons of force to the crowbar to try to open a window. The window pushes 500 newtons of force on the crowbar. Okay, so the crowbar has to push that window with 500 newtons of force. So the F sub E, the human effort, is 20. The machine's resistance is 500. And we want to know what is the mechanical advantage. So here's our triangle. We're going to cover up the MA, that's what we do not know. And then we just plug in our numbers here. So F sub R, this line means divided by, like it always has, F sub E. So we're going to do 500 divided by 20. And that is going to equal a mechanical advantage of 25. And that's the final answer. There is no unit because we divided newtons divided by newtons. So that unit canceled off. And so in this case, we have just the number. Let's look at another example problem. Find the effort force needed to lift a 2,000 Newton rock using a jack with a mechanical advantage of 10. Okay, so let's analyze what we know and what we need to know. So find the effort force. So this is our unknown. This is our unknown. This is what we're looking for. What is the human effort? We know our resistance force is 2,000 newtons. And we know that our mechanical advantage is 10. Okay, so since we have two forces, this is our triangle that we will use. We'll cover up that F sub E because that's what we don't know. And then this tells us that we need to do F sub R divided by the mechanical advantage. So now we can just plug our numbers in and solve. Okay, so 2,000 divided by 10 is 200. Okay, this time we are solving for a force, the effort force, and our force needs a unit, and the force's unit is always newtons. So our final answer would be 200 newtons. If you don't understand how I just did these two problems, if you're totally lost and confused, please get into contact with me and let me help you out, because up next is your chance to do some independent practice.